Hello, students. This is chapter 16, our star, the sun. The main topics covered in this chapter are the source of sun's heat and light, mathematical model of the sun, internal structure of the sun, sun's atmosphere, sun's corona and the solar winds, sunspots, the relationship between sunspots and the sun's magnetic field, and the magnetic reconnection, which can power immense solar eruptions. Here is some basic data about the sun. The distance of sun from the earth is 1 astronomical unit. The light travel time to the earth, it takes light 8.32 minutes to get from the sun to the earth. The mean angular diameter is 32 arc minutes, which is a little bit more than half a degree. The average angular diameter of the moon is 31 arc minutes. The radius of the sun is equal to 109 Earth radii. The mass of the sun is 3.33 times 10 to the 5 Earth masses. Composition, it's mostly hydrogen, some helium. By mass, the percentage of helium is more because helium is 4 times as heavy as hydrogen. By number of atoms, sun is made up of 92% hydrogen and 7.8% helium. The mean density is 1,410 kilogram per cubic meter. Mean temperature on the surface is 5,800 Kelvin. And in the center, it is 15 million Kelvin. The luminosity, that is the amount of energy that it emits per second, is 3.90 times 10 to the 26 watts. That means that many joules in every second. Distance from the center of galaxy, the sun or the whole solar system, is about 8,000 parsec away from the center of the Milky Way galaxy. Orbital period around the center of galaxy, 220 million years. So there was a big debate about the source of sun's energy. So the sun's visible surface temperature is 5,800 Kelvin, but inside it is millions of Kelvin. The state of matter, we normally talk about 3 states of matter: solid, liquid, and gas, but actually there are 7 states of matter, which are arrived at by either heating the material or by cooling and compacting material. So when you take gas and you heat it more and more, then the electrons are ripped out of the atoms, and then it becomes a sort of a gaseous mixture, a fluid mixture of charged particles or ions, and that is plasma. Plasma is different from gas in that it is very strongly affected by magnetic fields. So sun is made up of plasma. Early incorrect ideas. First, it was thought that the gravitation of the sun compresses the gas, and that compression causes heating by the Kelvin-Helmholtz contraction process. But later on, calculations suggested that this could not power the sun for as long as it has existed. Then another suggestion was thermonuclear reactions in the core of the sun. And in such reactions, mass is converted into energy. The famous Einstein's equation, E is equal to mc squared, tells you how mass could be converted into energy. c is the speed of light, which is a very big number, 3 times 10 to the 8. When you square it, it becomes 9 times 10 to the 16. So if a small amount of mass gets converted into energy, that gets multiplied to 9 times 10 to the 16, and that's how much energy is created. There is a nuclear reaction in which 4 nuclei of hydrogen come together to form a helium nucleus. Some mass is lost in this process, and that mass is converted into energy. There are two main kinds of nuclear reactions: fission reaction and thermonuclear fusion reaction. And the kind of reaction that happens in the sun is the thermonuclear reaction, which can only happen in conditions of very high heat and pressure. This is a more detailed step-by-step explanation of the process through which this combination of hydrogen nuclei into helium nucleus happens. It is called proton-proton chain. So there's so much hydrogen in the plasma of the sun, and that hydrogen atom is basically a proton and an electron. And then when it gets ionized, it loses its electrons. So hydrogen nuclei are basically protons. So these protons are at very high temperature, moving around very fast and bouncing with other hydrogen nuclei at very high speeds. And they are also compressed together. So sometimes they are able to overcome their repulsive force, and then two hydrogen nuclei combine. One of the protons loses its positive charge in the form of a positron and becomes a neutral neutron, and we get this isotope of hydrogen, which is called deuterium, which is made. In this process, heat energy in the form of gamma radiation is emitted. The positron combines with an electron, and further gamma radiation is released. And sorry, in the process of conversion of the proton into neutron, there's a neutrino that is released. Then this is called deuterium. Then the deuterium and another hydrogen nucleus combine together to form an isotope of helium, which is called tritium. It has 2 protons and 1 neutron. In this process, again, some gamma radiation and heat energy is released. And then 2 of such tritium nuclei combine together to form a helium nucleus and then liberate 2 protons. So in summary, what happens is 4 hydrogen nuclei or 4 protons come together to form a helium nucleus, and an immense amount of energy is released. This is the source of energy of the sun. Next, we'll look at a theoretical model of the sun. In this, we look at various points from the center of the sun moving outwards all the way to the surface, and we will look at the values of various properties such as temperature, density, pressure at various points. Also fraction of luminosity and fraction of mass. So on the top, we are starting from 0 and then increasing in 1/10. We are getting all the way to the surface. So first, let's look at the temperature. The temperature is highest in the center. It's 15.5 million kelvins. Then at 0.1 radius from the center, it is 13 million. Then it is 9.5 million. Then it is 6.7 million. and so on. And as you can see, as it gets further out, the temperature drops. The temperature drops very fast until at the surface it's 5,800 Kelvin. Similarly, density is very, very, very high at the center. It's 160,000 kilogram per cubic meter. To give you a sense of how high this density is, the density of iron is 8,000 kilogram per cubic meter. And so similarly, the density keeps on decreasing at about 0.5 radius. The density is 1,000 kg per cubic meter, which is the density of water. And then further out, it drops a lot. Similarly, pressure is very high in the center. The pressure here is not expressed in units of pressure, but in relative units. That means the highest pressure at the center is given a number 1, and then the others are ratios of the pressure to the pressure at the center. So as you can see, at 0.1 radius already, the relative pressure is 0.46. So it has already dropped to less than half of the pressure. And then similarly, it just keeps dropping very, 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 very fast. So the pressure at the surface is several orders of magnitude smaller than the pressure at the center. So these are somewhat easy to understand. Now there's the fraction of mass and fraction of luminosity. These are things which are cumulative, so that when we get to 0.3 radius, you have to imagine a sphere of 0.3, the radius of the sun, and within that, how much mass of the sun is concentrated. I say this is cumulative because the sphere of radius 0.2 and is inside the sphere of radius 0.3, and the sphere of radius 0.1 is inside the sphere of 0.2 radius and 0.3 radius. So each next one adds to the previous ones. Okay, so it's an addition. So you'll see that this increases very fast, and by the time we get to 0.7, the radius, it's 99% of the mass of the sun is located within that. And then beyond that, the pressure and density of the gas is just very low. So it may be, there may be a good amount of radius still to cover a good amount of volume, outer volume of the sun, but it's just very light and dense gas. So it doesn't contribute much mass. This point is important because somewhere between 70% to 80%, we could say the fraction of mass is almost 1 when rounded off. This will be important because there is an important demarcation line that appears at 0.75 of the radius of the sun. Now, when we look at fraction of luminosity again increases very fast. This is a measure of where the energy is being produced. So as soon as you go to 0.1, the radius of the sun, the amount of energy generated is already 42% of the total. And then at 0.2 and 0.3, by the time you get to 0.3, the radius of the sun, 100% of the energy is coming out from within that. So between 0.2 and 0.3 is another limit, which is 0.25 radius of the sun. So in fact, based on this, we make an internal structure of the sun, and we say that the internal structure of the sun has the thermonuclear energy core, which extends up to 0.25 radius of the sun. Then from 0.25 radius of the sun to 0.71 radius of the sun is a region called radiative zone. And then beyond that, from 0.7 radius of the sun to the surface is the convective zone. Okay. Here is a picture that shows that the names radiative zone and convective zone come from how the heat generated in the thermonuclear energy core is transferred to the outside. It is important to note that the thermonuclear energy core and the radiative zone of the sun act like a solid and spin together, whereas the convective zone has differential rotation, meaning it is more like a fluid, and different parts of it rotate at different rates. How do we know about the interior of the sun? We know about the interior of the sun by study of helioseismology. Just like we talked about in the chapter on Earth, the study of the earthquake waves tells us about the interior of the Earth. In the same way, it was noticed that the surface of the sun, or the body of the sun, is continuously having these explosions. These explosions produce waves, and it was found that the surface of the sun vibrates like a well, like a bell, rings like a bell. And by studying these different vibration patterns that are set up, we can study those, and we can hypothesize about the internal structure of the sun. And that's how we know that the internal structure of the sun is like this. Let's talk about something else, the external appearance of the sun. What we really see is a layer of the sun, which is called photosphere. So we say that the sun has a body, an internal structure, and the sun also has an atmosphere. And that atmosphere has three layers, starting from the lowest, moving out. They are photosphere, chromosphere, and corona. Chromosphere and corona are fairly transparent, so we can see all the way to photosphere. And so when we see the sun, what we mostly see is the photosphere. And this is what a photosphere looks like with the proper solar filter. And there's two things to notice. One is the sunspots that you can see. Second is the darkness on the outside near the periphery that you can see. This is called darkening of the limb. And this is something that scientists and astronomers take very seriously. This is not something trivial. This is important. If you think about it, although when we look at this, it looks like this is a shaded picture, a rendered picture of something that is round and spherical. So it would feel like this is just natural, but you have to realize that sun is glowing on its own, and anything that is glowing on its own doesn't have these different shades. Normally, if you look at a light bulb, it has equal glow on all sides. So scientists figured out the reason for this darkening of the limb. Basically, the outer part of the photosphere is colder and less bright, and the base of the photosphere is hotter and more bright. And so the light that is coming from the base of the photosphere has to come through the cooler outer part of the photosphere, and in that process gets absorbed and becomes a little bit dark. Towards the center, it has to travel through less thickness of the cooler photosphere, whereas near the periphery, it has to travel through larger thickness of it. And that is what causes the differentiation in the shades that we see. If we take a very powerful telescope and look closely at the surface of the sun, we find this granular structure. This granular structure is because of the convection cells that are produced. The hotter plasma from inside rises up, and it is more light colored in the center, and then it cools down and starts sinking at the boundary, and therefore it forms the darker boundary. So these are called solar granules. These are about 1,000 kilometers wide. These can be seen optically with a powerful telescope. Then there are some things called supergranules. Even larger scale convection cells are formed, which are called supergranules. These are not visible with the eye, but with instruments that measure the movement of the gas and plasma with Doppler effect, we can see areas of rising gas and sinking gas. Outside the photosphere is chromosphere. Chromosphere is given that name because it has this very unique pink purple type of color, and chrome means color, so that's why chromosphere. It has this color because of the a certain wavelength of 656.3 nanometers, which is the hydrogen emission, the H emission of the hydrogen at red wavelength of 656.3 nanometers. And then beyond that is corona. Here is the solar corona, and normally we don't see it because the photosphere is much more bright. But during a total solar eclipse is when the corona can be seen. The unearthly light of the corona is one of the most extraordinary aspects of experiencing a solar eclipse. Here is a schematic diagram. Comparatively, even though photosphere is the one that is most conspicuous and visible, it is the thinnest. It is only 400 kilometers in thickness, whereas comparatively the chromosphere average thickness is 2,000 kilometers, and it has these jets that rise up, which are called spicules, and they can go as high as 10,000 kilometers. Note for comparison that the diameter of the Earth is 12,000 kilometers. And then beyond the chromosphere is corona, which extends to millions of kilometers out into the space. There is a transition layer between the chromosphere and corona. In the transition region, the temperature changes and rises very fast. So there is a very unique and strange kind of happening that is taking place within the corona of the sun. Normally within stars and planets, as you go to the interior of them, of the bodies, the temperatures rise. But here the opposite happens. The temperature rises as we go from the chromosphere to corona. And this is something that has not been completely understood. And it is also a research problem that astronomers are working on, and it is called the coronal heating problem. It is thought that there are some magnetic and other kinds of processes that happen which produce more heat in the corona region. This shows how the temperature changes. In chromosphere, it is of the order of 10,000 Kelvin, whereas suddenly within the transition region, it changes from 10,000 to almost 1,000,000 kelvins in the corona. Here is a close-up shot of the sunspot. Sunspot has these properties. It has a darker region called umbra and a lighter region called penumbra, and the penumbra has this feather-like appearance. Also, sunspots tend to occur in pairs. Sun's outer surface has this differential rotation, which was observed from the time of Galileo. And from the time of Galileo himself and other Jesuit scientists, astronomers, were able to note that the sun rotates. And they noted that by observing the movement of the sunspots. And from that, they noticed that on an average, the sun completes one rotation in the period of about 1 month. The sun undergoes this an 11-year-long sunspot cycle. So the number of sunspots are not a permanent feature of the sun, but those are some things that form and then disappear, then form again. Those are like clouds in our atmosphere. They form, stay for some time, and then disappear. In the same way, the number of sunspots in the sun, uh, sometimes they are more, sometimes they are less. And they hit a peak after every 11 years. This is called the sunspot cycle, and that you can see from this figure. We'll talk later about the process that leads to this. This is a called a butterfly diagram. It's because of what it looks like. Looks like they are butterflies, but these are, if we track all the sunspots that are formed on the sun and against time, and also mark their locations, then this kind of structure is produced. But in general, this tells us that at the beginning of the 11-year cycle, the sunspots form near 30 degrees north and 30 degrees south latitude in the sun. And as time goes on, they move closer and closer to the equator as they approach towards the peak of the cycle, and then they disappear and then reappear again at 30-degree north and south. The sunspots are formed because of magnetic activity. So if we compare the sunspots with the magnetogram, we find that the regions where the sunspots are present, that's where very strong north and south magnetic fields are present. So what happens is that normally in the convective layer, the heat from the interior is constantly being transported to the surface and dissipated into the outer space constantly. However, charged particles and plasma have this property that they cannot move freely, and they get restricted in the presence of magnetic field. So whenever there are lines of magnetic field that are coming out of the photosphere, then in those regions, the charged particles cannot move as freely. And so the convection is disrupted, and so the heat is not transported so well to the surface, which makes those regions a little bit darker compared to the surroundings, and that's why they look like dark spots or sunspots. This is the rotation of the solar interior. The different colors show the different rates of rotation. The white is the fastest rate of rotation, and dark blue is the slowest rate of rotation. So you can see the fastest rotation is near the equator, and those parts of the sun can complete one rotation in 25 days, whereas the regions around the poles spin slowest and they take 35 days to complete one rotation. On an average, though, the interior of the sun, which consists of the thermonuclear energy core and the radiation zone, that doesn't have a differential rotation, that has a solid rotation. So all of it spins at the same rate, and it takes about 28 to 30 days to spin. So Babcock's magnetic dynamo model. The plasma is affected by magnetic fields, and the magnetic fields are in turn affected by the plasma. They get entangled within the plasma. At the start of the 11-year sunspot cycle, there are very nice and smooth magnetic fields that are set up within the sun from north to south. As time goes on, because the equator spins faster, those magnetic field lines get distorted. After 2 rotations and after 3 rotations, they start getting wound up like a spring. And after many, many rotations, they are wound up like a spring with a lot of energy stored in them. And then they start forming these kinks with the south and the north poking out of the photosphere and going back in. Those are the regions where transport of the convection is disrupted, and we have pairs of sunspots form. And then ultimately, the winding is so much that suddenly it breaks like a highly wound up spring. And we have times of huge solar storms and huge solar eruptions, and those are called solar maxima. And during this time, the whole magnetic field rearranges back to a more simpler form, like at the beginning. These series of steps and these diagrams are very important and commonly asked on tests and exams. So please practice drawing and labeling these. These are magnetic arches or solar prominences or coronal loops. Sometimes if the magnetic loops begin to pinch together, the field lines of the adjacent loops can reconnect, causing a release of energy. The upper helix or coil of magnetic field can break loose, carrying material into space. It carries material from the corona into the space. This is called coronal mass ejection, or CME. And when it is traveling, and if it happens to be directed towards the Earth and it hits the Earth's atmosphere, it causes a huge disturbance in the magnetic field of the Earth. This is called a geomagnetic storm. And during this time, we see many different effects. And one of the more visible effects is the northern lights. The northern lights are very strong in this time. And these coronal mass ejections and the solar winds, they keep happening, and they are very harmful to the Earth. But the Earth's magnetic field makes a protective boundary around the Earth and protects the Earth from these. So with that, we end the chapter on the sun.